So our next speaker is Lory Kadiyan from the Max-Planck-Institut for Mathematics in Bonn, and she's going to talk about the Lie algebroids of diffeological groupoids. So please.
Well, thank you. So first of all, I would like to thank the organizers for this workshop and for the opportunity that I can present my work. Today, I will talk about the algebroids of diffeological groupoids. This is still an ongoing work and will be part of my PhD thesis. Hence, it is joint work with my advisor, Christian Lohmann. So I was happy to listen to Joel's talk before this because it's in the same spirit, in the sense that we want to do some differentiation. Okay, so the outline of my talk goes as follows. We will first look at the general procedure of differentiation from from global geometric objects to their infinitesimal counterparts. Then we will look at the setting in which we want to do differentiation, mainly elastic diffeological groupoids. So the first two parts of my talk are going to be very brief because it's so it mainly comes from the mini course on diffeological groupoids by Christian. The third part will be the core of my talk, and there we will first look at the construction by Chevera of differentiating higher Lie groupoids to higher Lie algebroids. And then I will give you a categorical generalization of this method using the language of ends and coends. And in the last section, we're going to use this categorical generalization to define an infinitesimal counterpart of a diffeological groupoid and to see the formulation of that. So let's start with the first section. So in general, when one is interested in a differentiation procedure from global geometric objects to infinitesimal ones, one of the main approaches taken is the notion of smooth paths. This notion would lead to the notion of tangent vectors. For example, if you think of them as equivalence classes of paths tangent to each other, and this would lead to the notion of tangent spaces, tangent maps, and so on in the category infinite. Now, if we want to do differentiation, we would need a good differential calculus in our category. So for example, a Cartan calculus like we have seen previously, like the notion of vector fields, Lie derivatives, inner derivatives, and so on. Okay, so before we move on to the setting in which we will do differentiation, let's look at known examples of differentiation which use the notion of smooth paths. For example, let G be a Lie group. Its Lie algebroid is isomorphic as a vector space to the tangent space 2G at the identity. Now, more generally, if one considers a Lie groupoid G from G1 to G0, its infinitesimal counterpart, or its Lie algebroid, is defined by first taking the subbundle, so this TS of G1, the subbundle of the tangent bundle of G1, consisting of the vectors which are tangent to the source fibers, and then pulling it back via the identity, via the unit map. And that's going to be a bundle on G0, and the fibers will be the tangent spaces to the source fibers at the units. Now, these are examples in the finite dimensional setting. One might ask, okay, what about an example in the infinite dimensional setting? And we have seen, if you remember from the first lecture of Christian, that you can look, for example, at the diffeomorphism group of a finite dimensional smooth manifold, so diff of M. And you can ask, what is its Lie algebra? And it turns out that this is isomorphic to the space of vector fields on M, where here op just means that you take minus the actual Lie bracket of vector fields. And this, if you want to prove this isomorphism, one uses only the notion of smooth paths. Okay. That was a motivation, and now we look at diffeological groupoids. Okay, so our aim is to understand the Lie algebroid, or the infinitesimal counterpart of a diffeological groupoid, where we call a diffeological groupoid is a groupoid object internal to the category of diffeological spaces. Now, if you remember, like earlier today, we were talking of how to define or how to have a nice differential calculus in this category. And we ran into one problem, and that was that if you take the natural tangent functor on diffeological spaces, the one which was defined by left con-extending t hat after the Yoneda embedding, where t hat was the tangent function on Euclidean spaces via the Yoneda embedding. This is not always well behaved. For example, it does the left con extension doesn't commute with limits, and so we're going to get that it's not going to always commute with pullbacks, and hence this T is not going to give a so-called tangent structure to the category of diffeological spaces. And then we asked ourselves, okay, how can we fix this? Like, for example, you can ask what's the largest subcategory of diffeological spaces where T is a tangent functor. And we came to the notion of elastic diffeological spaces. And the main theorem was that the full subcategory of elastic diffeological spaces, together with the natural tangent functor, like defined above, is indeed a tangent category, and that it has a good differential calculus, which you have seen, Cartan calculus with the usual notions. Now, recall what is an elastic diffeological groupoid. So a diffeological groupoid is called elastic if you look at this nerve components, so GKs, which are given by this fiber product of G1s over G0 with respect to this left and right maps, have to be elastic themselves. Okay, for the lower degrees, it says that G0 and G1 are themselves elastic, and you ask that all the other fiber products are elastic as well. And this would be needed, for example, if you go to higher diffeological groupoids. And like this higher in the brackets, I will tell you in the end why it's standing there. Okay, and there was one nice surprising fact, if you remember, and that said that all diffeological groups are elastic. So like if you want to do differentiation of diffeological groups, then you don't have to restrict yourselves to some of the groups. They are all elastic, and they live in the correct setting to do differentiation. Okay. Now we go to the main part of this talk, and namely, we will look at a categorical generalization of Chevreul's construction. So firstly, in 2006, Chevreul has shown a method of differentiation from higherly groupoids to higherly algebroids, where by higherly groupoids, I mean simplicial manifolds which have some conditions. They can be differentiated to higherly algebroids, by which I mean differential graded manifolds. Now, in his method, the main ingredients he has used are the following. So he has used as an infinitesimal model R0, the so-called odd line, where recall R0 is just a it's the supermanifold, which has core the point space, and it has a ring of functions which are given by the algebra of dual numbers, but just as given by this graded symmetric algebra with one odd coordinate. So theta here has degree 1. Okay, and Chevreul has used a very important property of this odd line, namely, if you have a fixed supermanifold X, then you look at the inner home from R01 to X. So, like, I will first. Okay, wait, I will not write on it, but so I first consider the case for k equals to 1. Okay, and look at the inner home from R01 to X. That is representable, and it's representable by something very well known. It's namely represented by the odd tangent bundle of X. Now, one can use induction to prove that the inner home from R0k to X is also representable, and it's represented by the k iterated odd tangent bundle of X. This property is important. It has been some kind of a folklore in the history of supermanifolds, and yeah, using this, like you will see how we will make use of this. You get like nice other constructions. Another property is that there is a natural right action from the inner endomorphism group of R01. So this guy here on the inner home from R01 to X. And this right action is equivalent to the structure of a complex on the differential forms on X, and namely to its Z grading, so the degrees of the forms and the theorem differential. Now, this last part is important, and especially when you want to define V brackets and during the process of differentiation. However, in this talk, we're not going to talk about this anymore. Okay, so keep this second property in mind. That's the important thing. Okay, so let's look briefly at the Chevert construction. The setting is the following. So for a supermanifold N, we consider the surjective submersion with fibers R01, so this thing, and we look at the pair groupoid associated to this. And then we take the nerve of that pair groupoid. So you will get the following picture. Let me turn. Okay, so at the supermanifold of K simplices, this Pn R01 of K is just going to be product of K plus 1 copies of R01 times N, which is isomorphic to R0K plus 1 times N. And in this diagram below, you can see how the simplicial supermanifold looks like. So you always get one more copy of R01 as you go to higher degrees of your simplices, where the degeneracy maps are just given by diagonal map in a sense. So they just duplicate the odd coordinate of R0 at the right spot, and otherwise they would be the identity. And the phase maps are given by forgetting the ith copy of the odd coordinate of R01. And at the level of n's, nothing happens. The errors are all just identities. Okay, so that's your nerve. And now we look at the important definition. Okay, so let's start with a simplicial manifold, K dot. You should think of this as your hierarchy groupoid. Then the one jet of K0 is defined to be the presheaf on supermanifolds, which does the following. So it takes a supermanifold N, and it maps it to the set of morphisms in the category of simplicial supermanifold from this nerve we're talking about to K itself. Okay, now how you should think about this, the picture you should have in mind is this diagram here below. An element of this home set looks like the following. On the left-hand side, you have the nerve of the pair groupoid we were talking about. So you get always one more copy of R01. And on the right-hand side, you just have your simplicial manifold K. Okay, so these are your elements of this home set. Now, an interesting question is, when is this one jet representable? It's one question, and the other question would be, okay, if it's representable, then what is the representing object? So here's the theorem by Chevert, and it states that under some conditions, namely when your simplicial manifold has scan conditions plus when it's untruncated, then the one jet of K is representable. Okay, maybe this still sounds a bit abstract, but let's look at examples which you know. For example, let's look at the case of a Lie group. So if G is a Lie group and K is denoted by K to its nerve, then the one jet of K is precisely represented by the Lie algebra of G and well shifted by 1 degree. Okay, and if you go more generally to the case of a Lie groupoid, again, denote by K to be its nerve, then the one jet of K is represented by the Lie algebroid of G shifted by 1 degree. Okay, so this is a nice result. And now we want to keep this in mind and go a little bit to category theory, because our aim is to find or give a categorical generalization of this construction. Okay, so remember in the one jet of a simplicial manifold, there was this home set in simplicial supermanifolds. And so we want to look at functor categories, and specifically we want to look at morphisms in functor categories. Because remember, simplicial objects that we're working with, they are special functors. They are functors on the simplex category. So we want to look at a nice formulation of morphisms in functor categories. And here is the first remark from category theory. So assume that you have two categories C and D and take two functors F and G from C to D. Then the set of natural transformations from F to G is given by the following end. That's isomorphic to the following end, where the home functor inside the end is home functor in D, contravariant in the first argument, covariant in the second argument. So if you don't know anything about ends, don't worry, I will in a second give you a nice formulation of how you should think of them. Okay, so that's the first remark. And here is a nice result. You can find it in MacLane, for example. So the end of a functor is a special limit. So it's limit of, in this case, S so-called paragraph, and limit is indexed over the category, C paragraph, which is the subdivision category of C. But here I don't want to go into details, like what's this, what's the shape of this limit and so on. I just want to emphasize that ends are special limits. And so that's very nice because limits are something which you can compute, like if they exist and if they're nice enough. And knowing this fact, and knowing that the home functor preserves limits, we have the following lemma or corollary, and it states that basically home commutes with ends, or home commutes with integrals, however you want to think of it. So the home in D from D to an end is the same as the end of this home functor from D to S. Okay. Now we go to a small remark. And like I mentioned earlier, the functor categories we will be interested in are simplicial objects. And in fact, if you look at the nerve of a groupoid, that's going to be a 2 co-skeletal simplicial set. And you can take it as a definition that this would just mean that the home set in simplicial sets from A to X is in natural bijection with the home set in truncated simplicial sets from A to X, but restricted up to degree 2 up. Okay, that's just what 2 co-skeletal would mean. And so the objects that, or the functor categories we will be interested in are actually 2 truncated simplicial objects, and the ends that we're going to take are going to be over this 2 truncated simplex category, which is a full subcategory of delta with object 0, 1, 2. And that's good. That makes life a little bit easier because then in the end, the limits that we want to compute are going to be over smaller categories. Okay, but you will see later, like if you go a little bit to a higher setting, these 2 will be some M for some natural numbers, but still in our case, in the groupoid case, we have 2 truncation. Okay, so now we come to our main theorem. So remember the setting was that K is your like hierarchy groupoid. So in this case, it's your Kant simplicial manifold with which is M truncated and denote by. So in this case, Chevera says that the first jet of K is representable and denote by the representing object L of K. The theorem states that L of K is isomorphic to the following end. So it's the end over untruncated simplex category of this inner home functor, which, like we mentioned earlier, that's just the iterated tangent bundle or tangent bundle of Kn. Okay, now the first thing that you might ask is, okay, why does this first of all make sense? Like, what is the functor inside the end? Why is this a functor? So first we will look at a nice observation. And we will see that this iterated tangent, or the powers of tangent functor, actually gives you a co-simplicial structure. And then we're going to prove this theorem. So first let's look at this proposition. So if your supermanifold is fixed, so you have M as a supermanifold, then there is a co-simplicial structure on these powers of the tangent or tangent bundle. So n being mapped to the n+1 iterated or tangent bundle of M. Okay, so I will give you an idea like why we have a co-simplicial structure here. So we're going to explain what are these co-phase maps and co-degeneracy maps on these powers. So start with the nerve of the pair groupoid associated to R01. Which is depicted in this diagram. So at the level of n simplices, you just have product of R01, like n+1 copies. So you always get one more copy of R01, where the phase maps are the ones which forget the ith copy of your odd coordinate, and the degeneracy maps are the ones which duplicate the theta, the odd coordinate at the right spot, like we mentioned. So keep this nerve in mind, and let's look at the following diagram here below. So in this diagram here, on the left-hand side, you have the nerve of the pair groupoid of R01, like I mentioned. And on the right-hand side, you just have your fixed supermanifold M. And now you define your coface and codegeneracy maps as follows. So let's start with the coface map. So you want to go from something in the inner home from R0n to M to something higher, like something from R0n plus 1 to M. And the way you do it, so like look at this picture. If you start from something from R01 to M, you want to get something from R01 times R01 to M. So what you can do is you just pull back by the face maps of this nerve here. Okay, so that's why your DIs are going to be defined as pulling back the face maps of your nerve of pair groupoid of R01. Okay, in the same way for the degeneracy maps, if you want to go from R0 something higher, like n plus 1 to inner home from R0n to M, so let's say you're here at the top, and you want to go to something here, then what you do is you just pull back by the degeneracy maps of this nerve. Okay, and that's this definition. Okay, so that's the picture you should have in mind, and it's a very nice observation. I should also remark that this works in any tangent category. So if CET, now that you know what tangent categories are, is a tangent category and M is a fixed object in C, then there is a co-simplicial structure on the following. So on the powers of the tangent functor, which take n to Tn plus 1 of M. But here you have to make use of the monad structure of T. So the idea here is you view T as a monad and you define your co-simplicial structure, mainly your coface and codegeneracy maps, by using the multiplication mu and of your monad and eta, the unit of your T. Okay. So now we go to the proof of our main theorem. So remember, again, K dot is our Kant simplicial manifold, which is untruncated, and L of K denotes the representing object of K, J1 of K. And now, by definition of what it means to represent, there is a natural bijection for all supermanifolds between the following Hom sets. So here you just have the definition of a one-jet. So Homs in simplicial supermanifolds from this infinitesimal model to K. And on the right-hand side, you have Homs in supermanifolds from N to L of K. Okay, so now we're going to compute the left-hand side, and we will get the following. So this left-hand side is in natural bijection with the following end. This was just the formulation of morphisms and functor categories in terms of ends. And this is in bijection with the following end, where we just use the definition of an inner Hom to like spell out what happens in between. And as a last step, we use the fact that Hom commutes with n, so also with this integral, and we use the fact that the thing here in the integral makes sense, so because of the co-simplicial structure of the tangent functor, to write this isomorphism. Okay, and lastly, as you might have noticed, we use Yoneda to prove, so like we got that this right-hand side here is in natural bijection with this thing below. And using Yoneda, you can prove, you can say that L of K is isomorphic to this end here. Okay. Like some call this the ninja Yoneda lemma. If you look at the book by Lory Kadiyan, okay, it's mainly Yoneda. Okay, that's a nice result. But what I want to do here in the last part of this section is I want to spell this out, what happens to Lie groupoids shortly. So you have a picture in mind. So let's start with a Lie groupoid from G0 to, from G1 to G0 and denote by G dot to be its nerve. Okay, by using our theorem, we can write L of G by the following end. so the end of the inner home from R01 plus 1 to Gn. And by using proposition 1, which was a proposition saying that ends are special limits, we compute the limit, the associated limit of this end. And here we really make use of Maclane's formula of limits, like we compute the limit using products and equalizers, and we come to the following formulation. So this L of G will be isomorphic to the following. So inner home from R01 to G0 times, so the following fiber product, times home from R02 to G1 times home from R3 to G2 with respect to like these are I minus 1 i's. I mean, this sounds like a lot of formulas, but I will give you a picture now in the next slide so you can like, have a picture in mind of how you should think about this formula. And that's the following. So here I just spell out the inner homes in terms of the odd tangent bundles and powers of them. So L of G is going to be the odd tangent bundle of G0 and times the following. You should think of this formula by this picture. So this phi 0, phi 1, and phi 0, 0, phi 1, 1, phi 2, 2 are somehow your elements in these components here. But you require these phi's to, like you require these diagrams to commute. So you require commutativity with all the arrows that are appearing in this diagram. And the commutativity is depicted in these relations here, okay? These are really just the relations that you get by asking all these arrows to commute with every phase and degeneracy maps. Okay. And like I mentioned earlier, this, like in the case of Lie groups, this really gives you the algebra for Lie group, and for Lie groupoids, it gives the algebroid of Lie group or Lie groupoid. Okay, now having this in mind, we want to go to our last section, and we want to use our equipment to define the Lie algebroid or the infinitesimal counterpart of a diffeological groupoid. So here's our definition. Let G be an elastic diffeological groupoid, and let G dot be its nerve, then the diffeological algebroid of G is defined to be the following kind. And you mainly define it by this categorical like formula in terms of ends. Now I have to note that this definition makes sense because of the co-simplicial structure of powers of T, which we stated. We stated that this is true in any tangent category. Specifically, it's true for elastic diffeological spaces. So that's why this end makes sense. You might ask now, okay, why is this a good definition? And I will show that in the next slide. First of all, it's a categorical definition, but we can unpack it because the ends are special limits, and we compute the associated limit in terms of equalizers and products, and we get something very similar to the case of the groupoids. We get that D of G is given by the following fiber product, so T1 of G0 times T2 of G1 times T3 of G2 with respect to those relations. And now if you restrict yourselves to the case of a Lie groupoid, so if you take a Lie groupoid and view it as a diffeological groupoid, then you recover the same formula as before. So this Lie of G that we have here is really the same as L of G dot that we had before. So this explains, okay, why this could be a good definition. I want to end my talk with a few concluding remarks. The first one is that you might ask, okay, what would be the definition of a diffeological algebroid in terms of the usual way, like in terms of right invariant vector fields? But then here we need, first of all, the notion of what an abstract diffeological algebroid is. And for example, what's the notion of right invariance of vector fields and so on. This is still an ongoing work, like Christian was introducing it earlier today morning, and there's some work to be done here. So we also don't know if like our definition in terms of ends would give exactly would be exactly a definition in terms of right invariant vector fields, but maybe something closer. Okay, the next remark is that this categorical generalization we have also gives a way of constructing the infinitesimal objects of higher elastic diffeological groupoids. Remember, the original idea of Cervera was this differentiation from higher Lie groupoids to higher Lie algebroids. And so our construction would work in the higher case because your index category would then just be an M truncated simplex, the M truncated simplex category instead of the 2 truncated one. So it would work. And another comment or remark is that this construction also works in any tangent category, because we haven't used anything specific about elastic diffeological groupoids, except that the category of the full subcategory of elastic diffeological groupoids is a tangent category. It has a good differential calculus to start with. And lastly, the kinds of diffeological groupoids that we are going to be interested in comes from deformation theory. And that's why we're doing all this business. Okay, well, thank you very much for your attention.
Thank you very much. Are there any online questions first?
There's a question from Joel.
Okay.
Hi. So do you have any simplifications that happen when like the base of the diffeological groupoid is an honest manifold?
You mean just, and what is the base? Sorry?
When like the set, when like the diffeological space of objects is a manifold.
Well, we know the case of Lie groupoids, and there the base is a manifold.
Well, I mean, but the arrows maybe are allowed to be diffeological.
Okay. Not at the top of my head. But like when G1 is also a manifold, then sure, like I mentioned, it's just reduces to the case of Lie groupoids.
The reason I ask about it is because those are the examples that are relevant for like singular foliations and those kinds of things.
Yeah, good question. I don't know at the top of my head.
Okay, are there any more questions?
Question from Joel.
Hi, Lory. My question would be in the case of a one groupoid, but perhaps diffeological groupoid. I'm not sure I follow all the construction, but in which part would the bracket show up, and how? I mean, because I'm used to the bracket in terms of invariant vector fields. So how can we more or less visualize or imagine the bracket? I don't know if that's a bit vague, but I would love to imagine a bracket somehow.
Yeah, so I can tell you something about this. So like I mentioned, there is this right action from the inner endomorphism group on like this thing from the inner endomorphism group of R01 on like this, the inner home from R01 to X. And that's equivalent to the structure of the complex on the differential forms. And when you want to think about the brackets, you should think of them in this setting as degree 1 derivations on the ring of functions. And this really amounts to looking back at this action. And also the one jet I was talking about, it's not really a presheaf on supermanifolds, but it's a presheaf on supermanifolds with an action of the inner endomorphism group of R01. And so it's a presheaf on differential graded manifolds. And there you have the differential, so that encodes the bracket. So that's the way you should think about it.
I see, that makes sense. Thanks.
No problem.
When you talk about Homs in the category of supermanifolds, are the Homs graded? So degree preserving, or can they jump in degree? Sorry.
Yes, degree preserving.
Okay, thank you.
We have one more question.
So I have a question about the example of Lie groupoids. I think you gave it around page 25 or something like that. Could you go back to the slide where you
Yes
the nerve of a Lie groupoid, and then you say what well, this LG is.
Here, is this fine?
No.
Oh, wait, it's coming, sorry. Here.
Yeah, here. So, okay, you have this main formula. So here G is the nerve of a usual Lie groupoid. So the stuff on the right-hand side, that should somehow encode the Lie algebroid of this Lie groupoid, right?
Yes.
And how can I mean, is there a way to see how the Lie algebroid is hidden in the formula on the right-hand side? Or is there anything that hints to the Lie algebroid as we know it?
Yeah, so the way we have thought about this is to look what happens in local coordinates. And because every construction in local coordinates here is natural, so that's the way we have thought about this. And like in the case of Lie groups, it's simple because G0 is just a point. And then, like, remember Christian in the morning was giving a formulation of what the T does in Euclidean spaces and write it like in this smaller U0, U1, U2, and this differentiations. And you would do the same here and look at what happens in local coordinates to decode where the Lie algebroid here is. That's the approach we have taken. There is a bit of work to be done, but that's the idea.
Okay, thank you.
No problem.
Are there any more questions? Okay, if not, let's thank Lory again.